Okay. Hello, everyone. Welcome to today's installment of the Corundum developer meeting. Thank you very much for tuning in today. So I've got real quick announcements and status updates for today. So the next developer meeting is going to be on June 5th at 9 a.m. Oh, I forgot to update this slide again. We're dropping the 9 p.m. slot. So just June 5th at 9 a.m. And then the next Switch meeting will be um, get that right. Yeah, May 8th at 9 a.m. So if you're interested in Switch development and whatever Carlos has been working on, tune in a week for that. Um, and scheduling information is down below here. There's also a Google Calendar linked on the wiki page on the GitHub wiki. So if you want to add the events to your calendar, you can do that quite easily from there and keep up to date with everything. All right, so moving on to the status updates. So first I'm going to go over a little bit of the White Rabbit roadmap and some of the stuff that I've been mulling over, and then I've also got a couple slides on the OCP White Rabbit Nick project, including a couple of pictures for people that might be interested in that. All right, so White Rabbit. The idea is to integrate the White Rabbit functionality directly into the Corundum core logic. So for those of you that are not aware, White Rabbit is it's a very high precision time synchronization protocol that can operate at the, you know, tens of picoseconds or better level, as opposed to PTP that gets you down to, a couple of nanoseconds. Um, I guess White Rabbit has been integrated into PTP as a what do they call it? The PTP high resolution, I think, profile. So apparently there are a couple of minor differences at the protocol level, but it's basically the same functionality. So you can support both just with some differences in the software, basically. Um, so for this to work, to get timing precision down at the picosecond level, there's going to have to be some modifications made to various components that are associated with timing in Corundum, as well as the Mac and PCS logic that's actually handling the packets. Basically the connections between right at the edge with the serializers. And there's also probably going to be a need to have some sort of timing I/O subsystem. This can be used to generate and receive like 1 pulse per second signals, potentially standard frequencies like a 10 megahertz reference clock, and also potentially things like iRig, time code input output, things of that nature. Maybe even something that can talk to a GPS module. Not sure at this point exactly what the details might look like. I know there's a number of different boards that have SMA connectors and other stuff on there that could be useful to expose in a somewhat standardized way. So that's another thing that I'm starting to put some cycles into, as to what something like that might look like. It's one thing to be able to generate a 1 pulse per second signal, which we can do right now. I think the core hardware clock module outputs that, so that's pretty easy to route to a pin. There's also the PTP period output subsystem, but again, because that's kind of PTP clock cycle level, that's not necessarily going to be good enough for White Rabbit applications. So figuring out something that's going to be more precise and more generic is something that I'm working on. Um, but yeah, if we integrate the White Rabbit functionality more or less into the Corundum core logic, then we should be able to relatively easily add support for quite a few boards. Um, because this was something that the people were asking about at the Corundum, or not at the White Rabbit workshop at CERN. I guess that was in March. Um, Basically complaining that there weren't very many reference designs available. So, well, if we can turn Corundum into a reference design for White Rabbit, that could be quite useful, especially to support multiple different link rates. Because I think traditionally White Rabbit really only runs at 1 gigabit per second, at least if we're just talking about the White Rabbit switches that CERN has put together. But I think with Corundum, the idea should be to support 1 gig, 10 gig, and 25 gig. Um, so going into a little bit more low level here, for White Rabbit to run on a particular device or on a particular board, there's a number of things that are necessary. So one of them is board level stuff. They need the right clocking resources on the board, but then also on the FPGA, you need the right resources as well. Um, the SerDes, PHY, and MAC configuration is going to be very specific to the device family. So whenever you have integrated serializers, there's a question of, whether they're going to be deterministic enough to support White Rabbit. So, but within one device family, presumably all the performance is going to be the same. So you don't have to test every individual chip, but more like every FPGA series. So like, the Xilinx UltraScale Plus series or the Intel Stratix 10 series, for example. And each transceiver type, so GTH, GTY, GTM, etc. Or for the Intel devices, you've got the different tiles, right? The E tile, F tile, H tile, L tile, etc. If there's like hard MAC logic involved, then you also need to make sure that it's actually doing the timestamping correctly. So in some cases, for example, on the Intel devices with the E tiles that can work at 25 gig and at 100 gig, it's unclear at the moment whether or not they're doing the timestamping correctly with sufficient precision for White Rabbit. Probably good enough for PTP, but it might not be good enough for White Rabbit. So that could end up being a bit of a problem. We might need to bypass some of that hard logic in order to make this work. For the AMD Xilinx devices, GTX, GTH, and GTY, I think they're all very similar, and the current White Rabbit switches use these transceivers, so they should, with the quotes around should, work more or less out of the box without too much screwing around. They should be relatively well understood at this point. Other hardware, I think, is going to require characterization, so we'll cross that bridge when we get there, basically. So yeah, like I said, there's the hard logic. Okay, so there's potentially a couple different approaches depending on the device. You've got hard logic approaches where basically everything is done in hard logic, right? So you get the CMAC, E-tile, F-tile. That's going to require case-by-case characterization. If you use soft logic plus a serializer, then that potentially makes things a bit more straightforward because you can use the same soft logic on multiple devices. It's more down to whether the transceiver is going to do what you want. So for GTH and GTY, it should be reasonably doable for 10 gig and 25 gig. I've got some ideas for how to make that work at 1 gig, but that's going to require some experimentation. For all of the Intel devices, we'll see. H and L tile, I did take a look at that, and there are enough PLLs to be able to do concurrent 1 gig, 10 gig, 25 gig out of the same tile. There don't seem to be any restrictions on that, but obviously latency whatnot need to be investigated. And E-tile and F-tile, most likely these are going to be more restrictive, but we'll see. Also, the documentation is not necessarily as good for the Intel devices in terms of exactly what's going on in these tiles. So I definitely need to kind of follow up on that and figure out what might be possible there. And then I guess with the E and F tile, they have not just the actual serializers, but also the hardened MAC logic. So both of those are going to require investigation separately, I think. Because if the MAC logic doesn't work, maybe the transceivers could work if you bypass the MACs. But we'll have to see about that. All right, so I did a bit of ruminating on how to do 1 gig on the GTH and GTY transceivers. The real limitation here is more on the clocking resources side. So for those of you that aren't aware, the GTH and GTY transceivers are arranged in groups of 4 channels called quads. Each quad has one CLL, or has two QPLLs that are shared across the 4 channels, and then each channel has its own internal CPLL. So for boards that support 10 gig and 25 gig, that uses up both of the QPLLs. You need one for 10 and one for 25. Also on like the OCP White Rabbit NIC, we use one QPLL for 10 gig and the other QPLL for PCIe. So all of those are basically used in most cases. So that means, well, how do you do 1 gig? Well, the CPLL is only usable for 1 gig when the ref clock is 156 megahertz. Or this is a couple of other options, but it doesn't work at 161 or 322 because of a lack of divider settings in the CPLLs. So the question is it possible to use some other approach? For example, could we leave a transceiver configured for 10 gigs and do some sort of oversampling to get that that 1.25 gigabit per second link rate. It's not a nice oversampling ratio, it's about 8.25. It's unclear how that's going to be handled by the CDRs in the transceivers. A little bit of head scratching. I don't think it's going to work very well because that 8.25 is going to align with the edge detection logic in there in potentially a problematic way, which messes with the feedback. I think we have to test it and see, but first pass, I don't think it's going to work very well. One option, if the CDR is not going to work, is to basically put it in CDR hold mode and then effectively just recover the clock using barrel shifting, which in this case, I guess you wouldn't really be recovering the clock. It'd be more like recovering the data. So yeah, I don't know if that's necessarily going to work very well, at least in terms of getting White Rabbit working. But it also might be possible to override the CDR logic and adjust the RX phase interpolator via DRP. I think I found an app note talking about this. And I think also Xilinx has they have basically a soft burst mode PLL block, which can be used in association with the GTH and GTY transceivers. It's kind of intended for PON applications, but I think they might need to play around with the phase interpolator via DRP, so there might be something useful in there as well. But yeah, whatever approach, we need to evaluate the latency and variance and whatnot to make sure that it's actually going to be not just good enough to extract the data, which I think is doable, but good enough to actually run White Rabbit. So that I think there's at least one path here that should be reasonable for getting 1 gig working on these things. And also, I was doing some ruminating over, okay, if we do 1 gig, can we reuse the same MAC logic for 10 gig and 25 gig without having to have a whole separate 1 gig data path? And I think that should be doable. Basically, convert GMII to XGMII. You got to do some shifting of things around and whatnot. But if you do that, then you don't need a whole separate 1 gig MAC and separate data path. So I think that should be reasonable. Right. So the other thing is with ultra-scale devices, you can do 1.25 gigabits per second out of the normal LVDS I/O pins. And this is potentially quite useful because you can support a whole bunch of gigabit ports even on relatively low-end parts because you don't actually need the the GTH, GTY, GTX transceivers. There's a core available from Xilinx for SGMII and 1000 base X that uses the LVDS I/O. But the question is, okay, can we do White Rabbit on the LVDS I/O? Right? Because White Rabbit is not just about sending and receiving data, it's about figuring out this timing with very high precision. And this is where things get a little bit more murky at this point. But I think there's potentially a couple of different options. I'm suspecting that clocking resources could end up being a problem to limit the amount, to limit the scalability. So the nice thing about the LVDS I/O is you can fit, I think it's like 3 diff pairs per nibble group, which works out to 3 full, 1 gig ports per byte group. And I think there's 4 byte groups per IOB. So what does that work out to? I think that's what 12 ports per IOB. So you take something like the Korea K26 SOM. Can't remember exactly how many pins get pulled out of there, but something like 3 IOBs are actually exposed on the headers. So potentially you could support, what would that be, like 36 ports off of that thing, just based on the number of IO pins that are available. But I'm not sure it's going to be possible to do 36 White Rabbit ports. The question is, how many can we do, right? Can we do 4? Can we do 8? Can we do 16? Not sure. If we need like 1 MMCM per port, well, it only has 4 MMCMs, so that's a problem. So yeah, not sure what makes the most sense here, but this is something that I've been doing some ruminating on, so I'll present a couple of other details, right? So on the Xilinx devices, the LVDS I/O is handled by what's called the bit slice logic that's associated with the pins. There's actually 2 different ways you can use this I/O serialization capability, you can use either component mode or native mode. So native mode is the bit slices. Component mode is like the I/O SerDes and I/O delay blocks that you can drop down. As far as I can tell, it's implemented with the exact same silicon. It's basically the IOB logic that implements this. You can set it in two different modes. One of them is a native mode, the other one is a component mode. I don't know exactly what the limitations are of the component mode. It does seem like the bit slice can run faster, but they can both do 1.25 gigabits per second. So it might be necessary to investigate both of these and see what's possible. This logic is really intended more for things like high-speed memory interfaces, things like DDR4, where you have to run at a few gigabits per second per pin. They're not really intended for asynchronous serial communication like SGMII or 1000 base hex. um, but there are some ways of making that work. Um, let's see here. Just for comparison, this is what you have inside of like a GTH or GTY transceiver. Um, Inside, there's two phase interpolators and two samplers, and these will track they will track the edges, right? The edge sampler is looking at the edges, the data sampler is looking at the data. Um, the CDR FSM logic, it keeps a 90-degree phase offset between these two phase interpolators, and it compares what comes out of the data sampler with what comes out of the edge sampler to figure out whether it's running ahead or behind. So if you're interested in how this works, it's more straightforward than you might think, right? If you look at two adjacent data bits and it's 0, 0 or 1, 1, well, then there's no edge, so it doesn't matter. But if you say get 0, 1, then you know there's an edge. So you look at the edge, right? If you get 0, 1 on the data and the edge is 0, then you know that the edge flop captured it before the edge, so it was early. If it's 0, 1 and the edge reads as 1, then you know it captured late. Um, and the edge flop, that phase interpolator is running late versus what the data is doing. So, or versus the incoming data stream. So the CDR FSM will look at this information and adjust the taps on the phase interpolators to try and track the edges. And at the output of this, you get not only the recovered data, but you also get the recovered clock. And this is great because you can take this recovered clock and you can use, for White Rabbit, you can use the DDMTD to precisely measure what the phase offset is between the TX and the RX channels. But with the bit slice, they work in a completely different way. And I think in large part because of how the clock network works. So it's the PLLs that drive the IO components are located in the IOBs, and there's two PLLs for the entire IOB. And like I said, you can put like 12 channels potentially inside of the IOB. All of those 12 channels, you only have two PLLs. So one of them you could use for TX and the other one you could use for RX. So you can't track one, I mean, I guess you could track one channel, but you can't track all 12. So that's potentially a problem. For memory interfaces, this is fine because it's all going to be synchronous anyway with different delays, but it's potentially a problem if you have a bunch of independent serial streams. So the way the bit slice works for asynchronous serial is they use two bit slices to track the data. That's kind of similar to what the GTH and GTY transceivers are doing, where they're sort of tracking the data in the edges. It's not quite that simple, but that's kind of the idea. They like trade off under certain circumstances, and it's a little complicated, the details of how to actually make it work. But at the high level, they use two bit slices per input to track the data and to extract the data reliably. But it's not really a true CDR because they're not recovering the clock, right? They're just using the delay lines to delay the data going into these two bit slices. There's a shared IOB PLL and no phase interpolator to shift the clock. So the only thing they can do is shift the data to extract it. And then if there's a difference in rate between the rate of the actual data and the internal clock, then that gets handled by the gearbox. So effectively, what comes out of these two channels, depending on how things are being shifted around, they're either going to produce 3, 4, or 5 bits per clock cycle, which then the gearbox logic will accept and handle appropriately. So normally it should be 4, but if the clock frequency is slower, then it'll occasionally produce 3. If it's faster, then it'll occasionally produce 5. So it works, but it's unclear how. But at least at first pass, this is definitely not going to work with White Rabbit. At least, you know, you need some way to measure the delay, and these delay lines, unless you find a way to calibrate them across like PVT and whatnot, and even the tap sizes are relatively large. I can't remember what the size is off the top of my head. I think it's variable and around 40 picoseconds per tap, something like that. I don't think it's going to work out of the box very well for White Rabbit, unfortunately. So the question is, what options are there? If we want to do White Rabbit on BitSlice IO, what can we do? Well, one option that I have been mulling over is, well, can we do true CDR with the BitSlice IO? What do you need for that? Well, we took a look at what the GTH and GTY transceivers do, where they have the phase interpolator and they track the data and the edges. Well, you need a phase interpolator. You need 90 degrees from somewhere. We can get 90 degrees from one of the delay lines, I suppose. And then I think we have everything that we need. So downside is that you're limited in terms of the number of MMCMs. You need 1 MMCM per receiver, but there's only 4, so that means you can only do 4 ports total. But we also need a helper clock, which might consume an MMCM, so maybe we only get 3 ports. And also, I think because of the PLLs being associated with the IOBs, we might only be able to do 1 port per IOB. So that's not optimal, but at least it seems like you can get a couple of ports that way. But yeah, I don't think you're going to be able to do a lot better than that with the LVDS IO. On a part that has more MMCMs, might not be as big of an issue. So are there any other alternatives? Well, one thing that I was thinking of is it possible to use DDMTD on the actual data as opposed to on a recovered clock? One thing that I noticed is on the RX bit slice in 4-bit mode, they actually pass through the data combinatorially on a kind of a 5th output. So maybe you wonder, well, the timing information is going to be there in the data. So would it be possible to use the data stream itself as the clock for DDMTD or something similar to DDMTD? There is a way of doing DDMTD with clocks of different rates, basically by dividing everything to a common data rate. So the question is, well, could we do something like that where the division is effectively not constant but variable depending on what the data rate is? Could we do something like that and actually make that work to some extent, right? Could we use the data stream itself in place of the clock? Not sure at this point, but it looks like there's maybe a path here that could work. And if this works, then you wouldn't be limited by the number of MMCMs. You could actually put like 8 or 16 ports potentially even on a relatively small device. Just a question of, would this be possible? Not sure. But yeah, I guess the one thing to figure out here, well, there's a couple things to figure out. One is how would you do DDMTD with data instead of with the clock? I'm not sure if that's going to be possible. The other thing is to actually extract the information out of this, combinatorial output, because this is a pass through of the actual serial data, which is running at 1.25 gigabits per second. Fabric logic is only going to run at, maybe 300 megahertz or something, right, in 4-bit mode. So you'd have to use probably some sort of post-processing to figure out whether you actually have something usable, right? If you have, 3 or 4 transitions, you're in trouble. If you just have 1 transition, well, then you might be able to capture that and get some timing information from it. So I'm thinking it's going to have to be, some sort of post-processing to look at that and figure out whether there's a usable edge. But yeah, we'll see. I'm gonna continue ruminating on this, and maybe at some point I'll come up with some more concrete ideas for how to actually make this work. But it is at least, it seems like there's at least a possibility of making it work. Right. So finally, just to sum up on the Corundum and White Rabbit status, I'm working on the high-level architecture and also trying to figure out some of these implementation level um, considerations for how do we actually get this on, I'll get the functionality necessary on some of the devices that we're going to be working with here. And also there's I've also been taking a look at, all of the existing boards that Corundum runs on to figure out what's going to be reasonable to support White Rabbit on and what's going to require, a lot of hoops to jump through. um, the other thing that we've been working on is this Open Compute Project Time Appliances, or Open Compute Project Time Appliances project, open source White Rabbit NIC thing. The idea is to build a relatively low cost open source White Rabbit capable NIC. So for that, we're using a Xilinx Korea K26 system on module. And right now we have stock Corundum running on it. With once we get White Rabbit and potentially PTM implemented, then the idea is that all that will run on this card. So let me present a few more details about this thing because I mentioned it the last time, but didn't have any pictures of it handy or anything. So the initial version of it, the K26 SOM, it only has one GTH quad, so we got to use 2 lanes of that for PCIe, and then we use the other 2 lanes for 2 10 gig SFP pluses. And then the card's also going to have 1 or 2 1 gig SFPs wired to LVDS/IO. The initial prototype only has 1, but it looks like for the second revision, we're switching to a 4-slot cage, and we're going to wire up 2 slots. And then there's also a Renesas PLL chip, which is used for generating all of the necessary clocks as well as providing a tunable source. I guess there's also footprints for a couple of side time parts. I don't know if we're going to put those on there or if those are going to be build option or what. That's kind of TBD at this point. The main thing is to get the PLL working because it'll work without those oscillators, or should be able to work without those oscillators. Second revision is in the works. Should go to fab relatively soon, and there's been numerous fixes and adjustments on the board to correct problems that were discovered in the first revision, and then also to switch out the SFP cages and whatnot. So I have a couple pictures of the board here for people that are interested in this. This is what the board looks like with the K26 system on module. So we've got the 3 SFPs over here. These are 10 gig. This one at the bottom is 1 gig. There's 2 lanes of PCI Express down at the bottom. Now, since this is actually a Zinc system on module, it would be possible to run this standalone. So we put a couple of additional I/O connections here, USB port and a display port connector for just to facilitate that. There's a couple of timing I/O connections here. We got a nice little vertical USB-C connector for the USB JTAG. A couple other timing connectors on here that we've been experimenting with. PLL chip is over here. There's also a separate power input for if you wanted to run the card standalone. This is the card without the SOM. There's not much under the SOM at the moment. I'm not sure if that will change. The connectors on here are honestly not a huge fan of them. They're a little bit on the tall side, which I guess is both an advantage and a disadvantage. The advantage is that it gives you some clearance to put stuff under the SOM. The disadvantage is that the top of the SOM is basically maxing out the height of the card. So I think we'd have to like replace the heat spreader with this on the SOM with a heat sink in order to get proper cooling. Because if you wanted to fit this into a single slot, I don't think you can put an additional heat sink on top of the SOM. If these connectors were shorter, it might be a slightly different story, but it is what it is. This is the PLL chip over here, the IDT PLL chip. Well, it says IDT. I guess it's I guess this is a Renesas part, and that's it was IDT, and then they were acquired, something like that. Yeah, that's the top, and then this is the bottom of the board. There's some I2C infrastructure stuff here. The FTDI USB JTAG is over here. And then I had to make a number of fixes. This one was to get the PCI Express interface working because that was routed through the PLL chip. And for various reasons, that's not going to work. So that's one of the changes that has to be made on the new version. And then I also connected this little EEPROM here, which is for the PLL chip. I connected that to I2C. So um, that can be programmed directly from Linux without the PLL chip running. So with these two connections, I was able to program the EEPROM, get the PLL running, and then bring up the board. I guess I had to make a few other changes as well. There were some jumpers that had to be connected, and then I think I had to remove one or two termination resistors as well. And then also there was a minor fab problem. The little voltage regulator here was backwards, and that prevented the FTDI chip from working. So, interesting thing is, the regulator was actually fine. I turned it around and it just worked. So, the other thing is that the wiring for the JTAG connectors was screwed up. So the JTAG connectors didn't work, but the fortunately the FTDI part, once I turned around this regulator, did work. So I have actually been able to program this thing and test it out, and I've tested all three of the network interfaces and the PCI Express interface, and all that seems to work so far. So yeah, that's it for version 1, and then version 2 will be going to fab relatively soon. I don't know exactly when. We're working on that. And that shows up, I'll definitely let you guys know what the story is. Also, I think it's hilarious that there's a QC pass sticker on here, considering all of the modifications that had to be made. Probably a Fab House put that on. Anyway, that rounds it out for the slides I have. If anyone has any questions or comments, go ahead and fire away.
Uh, Thank you, Dr. Alex. Great talk.
Yeah, thanks for tuning
It's
in.
good. Yeah, it's good to see you're making efforts on these improvement on these hardcore things.
Yeah, I guess the White Rabbit stuff is quite interesting, but I guess there's a lot of stuff going on. So
Yeah, well,
seems like
but
you're
like,
more
yeah,
on the data path side, right?
right. But my question is, might be
Yeah,
a bit
sure.
of irrelevant information today. Yeah, yeah, I want to see if you're interested in adding a header data split feature in Corundum. So if you heard of it, so for those who don't know, header data split or HDS kind of allows you to divide TCP/IP header and payload in an Ethernet frame. So you store the header and payload at separate buffers.
Right. So this is in terms of when it's handed off to the network stack instead of having the
Right,
network stack try to extract the header.
right.
So for the HDS, would you be taking like the first n bytes, or would you actually do some kind of header parsing to figure out how big the header is?
We will have to do some header parsing because
Okay.
there are a lot of transport layer protocols, and there has been a couple of patches in Linux community that uses this feature to improve ARC's performance. Some zero copy receive. So in this regard,
It's worth thinking about. I guess we'd need a better understanding of what exactly is needed from the hardware for that to work, right? Because if it's just like the first n bytes, it's like, okay, that sounds like it'd be pretty simple. But if it's like, okay, we have to parse all these fields to figure out what's going on, that could be more complicated. Now, I have done some thinking about how that kind of a feature might work, because for um at least for future RDMA support, you'd probably need to process the header and the data separately anyway. So basically, my thought is to, in the data path, just duplicate the first, I don't know, 128 bytes of the packet or something like that. So the whole packet gets written into the internal RAM on the card, but then the header can be sent off for processing. And then, for the RDMA support, it would basically look at it and go, is this an RDMA header? If not, it would just receive it as a raw Ethernet frame. The whole frame is in the internal memory, so it can just receive the whole frame. If it parses the header and goes, oh, this is actually a Rocky frame, then it can figure out where the payload is, and then either process the frame and tell the data path to drop it, or figure out where the header is and then tell the DMA engine to do something with it. So potentially, when you parse the header, you could then tell the DMA engine to make, multiple transfers to write the header and the data to different portions of memory.
Yeah,
So something like that would be possible.
yeah,
I have to figure
that
out the
might be a good
mechanics
way to
because you
use it.
could actually have like another portion of you could have kind of like a header processing block, if you will, that gets all the headers from the transmit path and then has to make a decision of, process it and figure out, okay, are we doing one DMA operation? Are we doing multiple? Are we, have we handled this internally and we're just dropping it? That sort of thing, I think could potentially be doable. And then I guess if you have it separated out like that, then depending on what protocols you need to support, you can determine, what logic needs to go in there. It's like this is as soon as you start dealing with lots and lots of different protocols, and the logic complexity can really just, which is not so great. So, um,
Well, yeah, but definitely boost some performance. There are some commercial drivers have enabled HDS, for example, Broadcom and Mellanox, but I don't think Mellanox have done this for a Linux driver though. And anyways,
interesting.
I guess my question is actually more like a request for comment. I think to add this new feature, you know, this feature might benefit many research works like mine. So I am currently working on it, and I just want to know if you're interested. And if you do, I can keep you in the loop, maybe present
Yeah, yeah,
something
yeah.
once
I
I
mean,
make in progress.
if somebody's developing something as part of Corundum, I would definitely like to be kept in the loop as opposed to just having the thing dropped on top of me and go, well, how is this going to fit in with the rest of the system or whatever? So, um, because yeah, I've been thinking about how some of the stuff might work with Rocky going forward, where you actually have to handle more of the protocol on the FPGA. So, maybe we can kind of put some of those ideas together and massage something that's going to make
Yeah,
sense going forward for the overall design. So yeah,
right. But actually, my starting point is not in the context of Rocky. Rocky and standard Ethernet has completely
right.
different offloads. So, but definitely, maybe they can be massaged together. So,
Well, it's more just in terms of duplicating the header internally and then having a separate block look at the header and figure out kind of what to do based on the header. And it seems like it doesn't really matter what protocol you're doing, if it's Rocky versus TCP versus UDP, whatever. It's you're all gonna have always gonna have to do more or less the same thing, where you have to look at the header and figure out what to do. So basically, the
right. But
original idea that when I started thinking about, okay, how to implement RDMA, one idea is that you just send all of the incoming data to some Rocky block, and then that
mhm.
can do something with it. And if it's a raw Ethernet frame, then it can hand it off to the transmit path. But what I realized is that, well, you only need to deal with the header, and you can just let the the transmit or the normal data path handle the payload, and that'll just sit in its internal memory until the header processing is done, and you figure out what you're doing with the frame, and then you just tell the data path to drop it, to extract part of it and write it somewhere, or to and that seems like
So
it
you
should
just
it seems like that kind of functionality could work for this header separation as well. It's just you are going to send the header as well as the data, but they're going to go to different places, as opposed to Rocky. You won't be sending the header. You're either sending the whole frame because it's not a Rocky frame, or
yeah, yeah,
you're
yeah.
sending
I
the
mean,
payload to some random location in memory. So it's kind of a
yeah, I
kind of a
mean, it is.
similar
I
high
mean,
level
performance
functionality. Yeah,
wise, yeah, I mean, performance wise, the philosophy is the same, right? You want
yeah,
to do things asynchronously.
right.
Yeah. But I like to this specific topic, I'm not sure about duplicates. Maybe we can just add another layer on top of Mac and then let it parse the header and then decides which branch it goes to. Like, it doesn't have to be a duplicate header.
Well, I mean, the idea behind duplicating the header is then you don't really have multiple branches, right? The payload data, it's always following the same path. It comes in from the Mac, then it just gets written out the whole packet in one shot into the internal scratchpad RAM, and then the header gets peeled off, and you have a separate path that's doing the header processing, right? So if you were going to, I mean, if you had multiple paths, you'd have to parse into the header far enough to figure out, which path you're going to take. And then you'd have multiple data paths, presumably. And each one of those would have to handle the entire frame as opposed to just the header, which means you'd have to barrel shift the whole frame into alignment to take up a lot more space on the FPGA, that sort of thing. That's right. If the only thing that you need is like the first 100 bytes of the packet and the payload, you're not going to touch, um, aside from having the DMA engine transfer it. It doesn't make sense to be carrying around the whole packet.
Yeah. Like I said, if we constrain the scope to just uh make it useful in TCP/IP stack, there are not many protocols that you should take care of. It's just the IP protocol, and
Right.
it's
Okay.
not that hard to parse just the IP header. But you're right.
Right. Yeah. Yeah. I mean, I guess the thing that makes it somewhat more complicated is that, yeah, while the IP header itself is not that big of a deal, you might have one or more VLAN tags. You might have IP options. You might have TCP options. There's various things that will impact the length of the frame, and to separate the header
That
from the payload, yeah,
that is
that
true.
that that
But
could
I think we
complicate
can
things.
start with we don't have to start big. We can add constraints to it.
Right.
Say if you want to use this header data split feature, you should disable the IP options and stuff.
Right.
Yeah.
Yeah. Yeah. Oh, the other thing too is that the DMA engine in Corundum is capable of fully unaligned operations. So it can read from any offset in the internal RAM, basically, and then write that out anywhere in the host memory. So that functionality is already there. We might as well take advantage of it instead of adding a bunch of additional barrel shifting logic in the
Yeah,
fabric.
but actually, with respect to that, so actually, since we're like if you're enabling header data split feature, you basically have two rings per RxQ, right? And I think a
We
better
have
way
two
to
rings per
do,
RxQ. I guess I don't know how the header data split feature is implemented at the API level. I was under the impression that you would have multiple buffers attached to each descriptor, and the first buffer would get the header, and then the subsequent buffers would get the data.
oh
Okay, but it sounds like that's not how it works.
yeah, I'm thinking of from the perspective of application performance. So if you really want this header data split feature works to improve your performance, you're you want the data to bypass the copy in kernel and just to the application space. So you would have one space that stores the one ring that stores the header, and it will then goes to the kernel processing, and another ring that stores the payload, and it will later goes to the application space. And to do it, you would have to like designate register memory space prior to setting up the socket. So that would requires you to change some of the function calls you used in drive. For
Okay,
example,
so how does the
alloc.
card know which receive queue to use for the data?
Yeah, for now I'm thinking of using RFS, but as far as I know, we don't have RFS in Corundum.
Well, how do existing NICs do that?
RFS,
Okay.
yeah,
And okay, so this is looking at various fields in the packet to determine how to route
yeah,
the data.
yeah,
Okay.
yeah,
Well, maybe we need to implement that, right?
yeah.
Like what?
It's cool too.
Yeah, I mean, if this feature would kind of be built on top of that, maybe it's time to figure out how to implement that properly. So I don't know, what existing NICs support in terms of, what fields to look at and things of that nature, right? Can we kind of distill it down to its core? Because this is something that I've kind of been, you know, it's sort of like a more narrow version of like a match action table or something like that, right? If you can look at, arbitrary fields inside of the packet header and perform operations based off of that, um, doing that in general it can be quite complicated, but maybe it's worth spending some cycles on. So I don't know. Is that something that you've looked into? What existing NICs can do in terms of the RFS and what sort of configurability and matching capabilities are currently common and what would work well enough for your application?
Uh, yeah, something like that. But just kind of, I'm thinking right now. I'm just trying to rely on RFS and do this header data split feature. But it's good to see you're interested. I will definitely keep you in loop, and maybe we can talk a bit more offline.
Yeah, okay.
Yeah,
Yeah, because it sounds like you need not only the header data split but also the filtering, right?
yeah,
Having
yeah.
the header data split without the filtering is not going to do much, basically.
Mm,
So okay, so I guess there's kind of two things that would need to be implemented for that: the filtering and yeah, okay. So we'll have to figure out how that's going to work. Um, I guess it makes. I mean, but does that? I guess there's other things that would make use of the RFS as well. So I think XDP sockets can do similar things, or they kind of need to take advantage of similar filtering capabilities, right? So if you open like an XDP socket and you want to receive, at the application level and bypass the kernel, you also need that filtering capability. So
but they're doing software though,
XDP.
right? The XDP filtering, isn't it?
Well, okay, so I guess the problem with XDP is that it's kind of an overloaded term. There's XDP, which is the you can attach little software programs effectively at a low level in the networking stack. But then there's also AFXDP sockets, which presumably can be passed all the way through to the hardware. So you'd have to do the filtering in the hardware. But it's the idea with
Oh,
the AFXDP sockets is it's kind of like DPDK but built into the Linux
I
kernel.
know,
You're
I know
bypassing
what you're talking about. Yeah,
most of the kernel stack. Um, so in that case, you can't use an XDP program in software because you have to make the decision of which queue to put the packet in hardware. Seems like it would basically be doing something similar to the header data separation because you're trying to basically connect a hardware queue to a single socket or a single software application. But I
true.
guess the difference is how the headers are handled, right? With AFXDP, you get the whole frame. With
Yeah,
with the header splitting, you're just getting the
the kernel gets
payload,
it.
and
Yeah,
then the kernel
yeah.
gets yeah. So actually, here's an interesting question: with the splitting, do you have to remove the header so the application is not allowed to see the header?
Not necessarily. Maybe you can just copy the header because headers are small, but it's better to completely get rid of the header before you move it to the application.
Right. Okay. Well, and I guess the other question is, what would the kernel do with the headers, right? If the application already has the data, what would the kernel be
Uh,
doing with the header?
it well, the kernel definitely prevents the application to see the payload before it finishes processing with the header.
Ah, okay, I see. So
Yeah,
the
yeah,
okay, so basically the kernel is still running the network stack more or less
yeah,
normally,
yeah,
um, but it's just the application data gets sent to the application first,
yeah.
or it gets
So
sent
you
directly
save
to
the
the
copy.
application buffer, so it's already there once the kernel
Hmm.
determines that yes, that packet is actually for this application. Okay, I guess another question is, what about things like checksumming and such? Um,
I think you have hardware offload for checksum already.
Yeah, I guess in the receive path we do have a checksum over the whole packet. Yeah, so I guess the kernel doesn't have to look at the full packet contents to do its checksum computations.
Yeah,
Okay. All right. Yeah, so I guess if we get RFS working, so I'm just trying to figure out what's going to be a reasonable roadmap for getting all of this operational. It almost seems like if we can get the receive flow steering stuff working, it might make sense to take like an intermediary step of, implementing AFXDP sockets, or at least to take a quick look at that, because that's more or less doing the same thing. You're just handing the whole pack to it seems simpler, right, than to try to glue together multiple queues. So we can use that as kind of an intermediate step, make sure that works, And then we can look at, okay, well, if you're going to peel off the header and send that to the kernel, and then also keep track of the data, how that would work. So yeah.
Yeah, so in short, filter first and split later.
Right. Yeah. Well, that's quite a bit of work, but we can discuss that in more detail maybe as we start to get up to speed with all of these pieces. So yeah. So I think since all of this is going to need RFS, it probably makes sense to take a look at RFS first and figure out, what are other NICs doing? What kind of configurability is there? What does it make sense to implement in Corundum? And, just take a look at that, because without RFS, nothing else makes sense along this line. So, what do you think? Work on RFS first. We'll see if we can get that working, and then the next step
if
is
from my perspective, I definitely want to see some of my experiments result first. So I would assume that that all traffic needs to be header data split first, so that I can get some of the raw metrics first, and then if that works, I think you can move on to how to filter the traffic to see which queue they go to. What do you think?
Well, I guess that's going to require some ruminating then. I don't know. Basically, from my point of view, I don't know how it's like the queue selection part is quite important, right? Because otherwise, without queue selection, you can only send everything to one queue, and that's probably not going to help your performance very much, right? You can't open multiple connections if you don't have any kind of logic that's doing the flow steering. So just, or at least figuring out how that functionality could work at the high level, even if you're going to implement kind of a mocked up, simplified version of it, I think is quite important.
Okay.
But we can discuss that in more detail offline, perhaps. Well, so you want to get some measurements. So other NICs implement this, but you want to do something more specialized or something different? Like what's
Like Mellanox has this feature, but they have a document about HDS, but in Linux. I mean in Windows, not in Linux.
Oh, interesting. Okay.
So yeah, I think some of the virtual NICs has this feature. Also, Broadcom NIC has this feature, but unfortunately, we don't have Broadcom NIC. So I only have Mellanox. So I want to do it in
I see.
Corundum and see.
Okay, so you want to experiment with it, but it's not a feature that you have access to on existing NICs. Okay. All right. Well, we can certainly discuss that in more detail and figure out what might be the best course of action. So, all right.
Yeah.
Sounds good. Do we have any other questions or comments? I see Krishnan has joined us.
Oh, sorry.
Hey,
Think
how's
I
it going?
missed most of the meeting. Good,
That's all
good.
right.
Uh,
Just missed me talking
so
about
yeah, I
White Rabbit
do
a bit, which might not be interesting.
certainly. If I understand some of it, some part of it, it would be more interesting though. Currently, I do not. Yeah, I lack some understanding towards that project, I guess.
Right. Well, you can watch the recording, I suppose. I'll
Yeah.
get that uploaded
So
soon, and people can take a look. Anyway.
I had this question. So I was working on a specific part of OpenNIC,
Mm-hmm.
and there was this 250 megahertz axis stream bus.
Mm-hmm.
And what I was trying to do is I was trying to get some data, and I was trying to write to the DDR. The same thing I was trying to do, if you remember. So I solved it, but in the end, I had to write my own FIFO with independent clocks, because the Axie FIFO from Xilinx kind of doesn't really, I don't know how to make it work. Like, I think there's supposed to be, it needs a locked face or something like that to really get something out of on the other side. But I really couldn't work with that.
So you're talking about AXI, not AXI Stream, right? The memory mapped version.
It's Axie Stream, not the memory map.
Okay.
Axie Stream FIFO.
Okay. So you use
Independent
mine
clocks.
instead of the Xilinx ones because you couldn't figure out how to make
No,
the
I
Xilinx FIFO work? That's interesting.
no, I didn't use yours as well.
Oh,
Because the thing is, I was also doing something on the packet, and I was also doing something on the packet, so it has to be glued with the logic, So the upper logic needs to say to the FIFO when it can, move the pointer. Otherwise, it was just overriding the data
yeah.
and stuff like that. Because the whole problem was the DDR works on a different rate.
Right. The DDR has its own internal clock. So
Yeah,
you
and
have to
it's
cross
not
into that
divisible.
domain. Yeah. And it's what?
Yes, it is not divisible. Like, it's not like, okay,
Yeah.
125, 250, things like that.
Yeah.
It's
So
very
you
weird
need an
clock. So
asynchronous FIFO to transfer it across. Yeah.
yeah, so that was a thing out of the way.
So you said you built your own FIFO for that?
Yeah,
And you got it working. Okay. Eventually.
that was a lot of
Yeah.
work. Also, the thing is to get the simulation working with the whole OpenNIC. I don't know how you did it, but I see that OpenNIC people kind of cited your test benches on the GitHub page itself.
Yeah, they borrowed a bunch of my stuff.
Yeah, but I never tried to test that test bench.
Right, but I
with the
think
OpenNIC.
their test code, it's really only like for the application block, basically. It doesn't simulate the whole design. As at least in terms of, I think I looked at that a while ago, but yeah, they only simulate a part of the design. They don't simulate the whole thing. Like with Corundum, it simulates basically everything except the PCIe hard IP core. But there's no easy way to do that, to simulate the whole thing with the QDMA IP core in Coco TV. So I think they do a much more limited simulation of basically just the application section. But it's also been a while since I looked at their code. Maybe they've changed something up.
Mm-hmm.
And I'm also not sure what simulator they'd be using, because I know Coco TV doesn't support the Movado simulator. Maybe they're using Model Sim or something.
Yeah, they're using Model Sim.
Yeah,
So
I mean, in principle, it should be possible to simulate the whole thing. But yeah, I guess to simulate all the DMA code as well, that adds a lot of additional complexity. I guess one advantage of the way Corundum is put together is you can simulate basically just the DMA engine without the PCIe IP core, so that simplifies the what's being simulated a bit, which makes it a little bit easier. Versus, I don't know if you can simulate like the QDMA IP core without also simulating the PCIe IP core inside of it. And I think that model is pretty complicated, so it really slows things down.
Mm-hmm. Also, I had I sent a message on the forum as well. So so far I've been testing 100 gig with DPDK,
Mm-hmm.
and
This is with OpenNIC?
because no, so I use, so my standard test bench just have Mellanox connector
Yeah.
with each other. So I know things are working, and then the other ports of Mellanox is connected to FPGA U280 basically. And I have tested Corundum as well. But usually I flash OpenNIC, yes. And so I use a patched version of DPDK for OpenEC. I don't use QTMA drivers, or I just started with DPDK.
Right.
And I had a lot of so yeah, PyPerf didn't work out of the box, so I used to use DPDK, and I am able to test it, but now I'm at a stage where I need to send an actual payload,
Mm-hmm.
and my application code is not working reliably.
You need to send an
Uh,
application. You need to send a payload from DPDK or from the FPGA,
yes,
or
yes,
from
DPDK
DPDK.
to FPGA,
Okay.
DPDK to FPGA. So I kind of started working with package.gen, but even package.gen can have it has very limited user support for user payload bytes, basically.
Yeah, I guess at some
So
point you
you
might
can
just need to write a little DPDK app to do what you want. I honestly have not used DPDK very much, so I'm not sure the best approach for doing that. But
Mhm.
potentially what you could even do is take like one of the DPDK utilities like package.gen, make a copy of it, strip it down,
Yeah,
and then add the
yeah,
functionality that you need to it, right? There's probably some pretty good examples for DPD applications that you can build on top of. So
mhm. Okay. Yeah,
yeah,
that is what
so it's like at some
I'm
point it's
planning to
just
do.
like, well, you can use standard tools, but they can have their limitations. So at some point you might need to sit down and put together something custom, because eventually that's probably what you're gonna have to do, right? Have a little DPDK app that
Right,
can talk to your card. So
right. Yeah, that is because my app is like it's kind of crashing my PCI bus. I don't know why is that, but so I thought, okay, maybe move to a better reliable code.
well, what's crashing the computer?
So I have an application code which directly takes a DPDK library and
Yeah.
use the RT functions and so on. But for smaller chunks, it works fine. But huge payloads, it just crashes. So sometimes I'm doing something very wrong, basically. It's just a very naive way of
Well,
code.
define huge.
400 kilobytes.
Hmm. So you're trying to send that with the OpenNIC, or
To a FPGA which is flashed with OpenECS.
you're trying to send that as a single packet?
Uh, no, as uh 60, 64 bytes of packet.
As a whole bunch of 64-byte packets.
Yeah.
Okay, that seems weird. Yeah,
Yeah.
but I'm not sure
So
exactly what's going on behind the scenes for handing that off to the card, right? Because you can set aside a big buffer, but then if you want to send a bunch of small frames out of that, the card needs to know where all the individual frames are. Seems like the DVDK driver should handle that and hand it off to QDMA. But at the same time, even if it gets it wrong, I don't know why it would crash the whole system, unless there's a bug in QDMA, which I guess that's possible.
yeah, that is very possible. I agree with you. But at some point, I remember, so it always crashed. But at some point, I saw dead beef from PCI bus. So what I do is I uh, I do reset. I remove the F, so after flashing once, it never. So whatever I send, there's no effect. Actually, there is no more payloads sent to the FPGA. So I remove the FPGA, I rescan the PCI bus, so it plugs back in, and then that is how I reset the FPGA basically. So when I did that, uh, it just crashes.
Yeah, that's a problem.
So yeah, so I'm thinking to move something like to a package or something like that, and see how far it goes.
Yeah. I guess we'll see how that works. Yeah, I don't have much experience working with OpenNIC or QDMA either, so I don't really have any, much insight to help debug that. So, um, I know there have been a couple of projects to put together a DPDK driver for Corundum, but they might be a little bit out of date at the moment. That could be another option to consider as well if you need DPDK, or might be able to work directly with Corundum as another option. I don't know. I guess it depends on what the high level functionality is that you need to implement. So I think you discussed a little bit about I think virtualization, right? You were doing something along those
Partial
lines.
partial reconfiguration,
SRIOV
yeah.
or yeah,
No, partial reconfiguration.
partial reconfiguration. Ah, okay.
So basically need to send the bit streams to the memory somewhere where you can
Right. Okay. You
kind
need to
of,
transfer the bit stream to the card and then transfer it
yes,
into the
and
PR region or whatever. Okay.
yeah, kind of trigger that from the maybe from the on the network or from the host, whatever.
Yeah. So a colleague of mine did a lot of work with partial reconfiguration. Also doing something with Corundum actually. Basically, the idea was to put down a bunch of RISC-V cores on the FPGA, each one in its own little partial reconfiguration region, and then be able to swap those out on the fly. So
Right,
so each
right,
core wouldn't be just a core, but there would be a core plus some
right.
additional logic. And it was a complete nightmare.
Yeah,
Lot of
it's actually
wrestling
very
with
difficult.
Vivado to actually get things to close timing and whatnot. So, um, yeah,
So
I
so
kind of
my
avoid partial reconfiguration unless it's absolutely necessary. So, unfortunately, as researchers, that can be kind of the whole point is, hey, we want to reconfigure this dynamically. It's like, all right. I
so
guess then a
currently my
colleague of mine
setup
was
work.
also doing more complicated partial reconfiguration stuff on various Xilinx FPGAs, and they did a lot of work on figuring out how the partial reconfiguration process works. Um, I can't remember the specifics on that right now,
Mhm,
but they were trying to do something a lot more complicated. Yeah, I'm not sure what the status of that project was and how far along they got with it, but
mhm.
yeah, it's partial reconfiguration is tricky to make work properly. That's also if you screw up the partial reconfiguration, then it can, well, it's not necessarily going to like break the FPGA, but it'll screw up the design. You'll have to reload it from flash or whatever. Um, like with partial reconfiguration, you got to make sure that the bit streams are compatible with each other, right? That the image you're loading has to be compatible with the base image that's on the device. I don't think there's
Yeah.
any like explicit checks to make sure that, at the device
No.
level to make sure that
Uh,
works. So if you mess it up, then you can end up with a screwed up device, and then you'll have to reset it, which is not so great.
yeah. So I was able to get it working actually.
Okay.
That is why I'm kind of stuck with the OpenNIC project because I started with it and I
Right.
could
Yeah.
yeah. So this is the end part, I guess. If I be able to figure out this host situation, I think it will work. No. Also, I'm trying to build some extra circuitry in the framework to measure basically like performance counters or something like
Right.
that sort to measure the you know what process goes when and things like that.
Right. Yeah, it's definitely a lot more accurate to do that in the hardware than to try to do that with software counters. So that's definitely the way to
Right.
go.
Right. Okay. How's it going? How's it going there? Good.
Yeah. Yeah, chipping away at stuff, it's how it works. So yeah, there's a couple other things I need to finish getting implemented in the Corundum scheduling layer. Uh, Hopefully I'll be able to get that squared away soon. It's one of these things, there's like a whole bunch of requirements that all have to be met at the same time, and figuring out how to write code to do that is tricky. So once I get that sorted out, then we'll have a new version of Corundum with some of these new capabilities, and that should be good. And then I guess another thing that I talked about as well at previous meeting was potentially, switching languages and licenses. So I need to do a little
Right.
bit more. I haven't heard much feedback on that side. So
Right.
I know some people would really like to see things in System Verilog. I agree with that. Haven't heard much feedback on the licensing side. We'll see. I think I might need to make some posts somewhere and see what the community in general thinks about System Verilog best practices and also the license question. So hopefully in the next couple of months we'll be able to move that stuff over, and that should be good.
Right. Right. I agree.
All right.
But I don't mind Verilog, but
Well, right. Yeah,
it's
it's just it's in some sense not that big of a deal, but in the other sense, there's I know that there's people that are avoiding projects written in Verilog because it's old. So yeah. And it does provide using System Verilog definitely does have some advantages, right, in terms of code size and whatnot. So definitely something I'd like to explore. But the other aspect of migrating from Verilog to System Verilog is that since I haven't really worked on a big System Verilog project before, and I'm not super familiar with the ins and outs and advantages and disadvantages of various ways of doing things, it's kind of hard to just hey, we're going to pull the trigger on this and port it over, because you could make a decision in terms of how you design one of the interfaces, and then it ends up being a huge problem later, and then you got to go
right.
report a bunch of stuff. So yeah, I should probably make a post. Maybe I'll do that. Maybe I'll do that the next day or two to ask about best practices for System Verilog. So the other thing with System Verilog is that you can run into tooling issues, right, with certain tools not supporting certain features or not handling certain features correctly. So might need to do some working around of tool problems. So it makes sense to talk to people that are using System Verilog and just get a heads up on what some of those potential pitfalls might be.
Right.
We'll see. So were you doing anything with Corundum right now, or you're mainly just using OpenNIC?
So I'm planning to move. It's just the current project is on a deadline.
Right. Yeah,
And
you got to get the current thing
it's
working first before you start,
yeah.
rebuilding everything.
Yeah. I certainly so the thing is about this concept, right? If this concept didn't work on so this idea has to work before so it's in the pipeline. I did all the testing and I have all the setup and everything running.
Yeah.
But I have to sit one day and do it. Make the move. But I got little so uh, I know because I still need to spend some time into understanding if I can just straight away get an axis stream from the packet, because my current work is just so good thing is it's just a module, right? It's just an
Right.
IP. If I just plug my IP, things work. I don't think there is any other issue. It's just the framework I have to figure out a little bit.
All right. Well,
Yeah.
that sounds promising.
So yeah. So I'll soon move shift and I'll let you know.
Right. It'd also be interesting to compare between the two to see performance-wise and whatnot.
Yeah. So one of the questions that I wanted to ask you, how did you test Corundum for 100 gig? Did you use IPv3 with the current branch, or what did you use?
Right. So I actually have a little test script in the repository that I use that spins up a bunch of iperf instances.
Right. IPv3.
And it runs a few things. Yeah. So I think
Okay.
the test script, it runs, so it collects a bunch of information, which is not really part of the actual testing, but it's just, good to know, so I can go back. If something weird happened, then I can go look at some of the logs and whatnot that it collects. But then for the main part of the testing, it runs Linux PTP, just to make sure that the time sync is doing something sensible. And then it also runs, I think, iPerf3, yeah. And it runs iPerf3 in both directions. So it runs varying numbers in transmit, varying numbers in receive, and then varying numbers with both transmit and receive running at the same time. So it just kind of does a sweep, and then it writes out a CS or writes out a bunch of data files. I guess there's some CSV files with the bandwidth figures, and then I have a plotting script which makes a pretty graph out of that. So yeah, that's usually what I do, and yeah, depending on like the packet size settings, you can get, full line rate with just a handful of iPerf processes. I think it's like maybe 3 or 4 iPerf processes to get pretty close to 100 gig for either just TX or RX separately.
Right.
Because one of them will do like, maybe 40, 50 gigs, something like that. With jumbo frames, with 1500 byte frames, I think it tops out at like 85 gigabits per second, something like that. So there's still some optimization to do there, but yeah. Yeah, because Corundum right now doesn't do any kind of hardware segmentation offloading. So that would definitely help with minimum length frames. And there's also some optimizations in the driver that could probably be done to improve performance as well. But yeah. At some point we'll make that work. It adds quite a bit of additional complexity. So
okay.
Anyway, do you have any other questions or comments, or does anyone else have any other questions or comments?
Nothing for me. Thank you.
Nothing from you? All right. Cool.
Yeah, I still have to go through the documentation for a little bit more before I can.
Yeah, sure. And if you have any questions, feel free to ask questions on the Zulip instance.
Much appreciated.
There's some helpful people on there. I'll help you if I can, but there's also other people on there that can be helpful as well. So
yeah, I understand.
Yeah. All right.
All right.
Well,
have a good day, I guess.
If that's everything, then I guess I'll see you guys at a future meeting. Maybe I'll come to a Switch meeting, or maybe the next developer meeting in a month, or I'll see you on Zulip. Anyway,
All right, see ya.
Talk to you guys later. Thanks for tuning in.
Thank you.